Hi, my name is Brian Tay, and my FYP title is the study of quantum cryptography protocols for secure quantum communication. This project is under the collaboration with Professor Raymond Uy. There are two objectives that we want to achieve today. The first one is to give an overview of quantum cryptography, and the second one is to understand quantum cryptography via some simulation. To achieve our objective, first we will look at one-time pad, and after that we will look at BPM92 protocols, and then after that we will look at some overview of it, for example entanglement and teleportation. Then we will do some simulation, and lastly we will come to a conclusion. In order to understand quantum cryptography, we first need to understand one-time pad. Suppose I give you 4 totally random characters, and my question is guess the word that is in my mind. You may come up with the word NINE, 9, or you can come out with the word 5, but no, both are wrong. The word that is in my mind is 4. Well, from this small experiment, we see that as long as we can have a totally random one-time pad, which is RBHI, we can theoretically create unconditionally secure cryptography. Now, there's an asterisk on the word random because what if the one-time pad is not fully random? And for Alice, they may ask a question: how can she send the one-time pad to Bob securely? And these are the two questions that we will be trying to solve using quantum cryptography. To understand BPM92 protocol, so we will start with a satellite sending two entangled photons to Alice and Bob, and we'll call them EPR A and EPR B. Alice will entangle her pair of EPR A with a secret message she wants to send. Let's say it's a message called 4, and measure them. Once she measured it, she'll get a result of 0, 0, 0, 1, 1, 0, and 1, 1. And this classically encoded message can be sent via optical fiber to Bob, which Bob can use them to apply some kind of transformation onto his pair of EPR to get the message 4 that Alice wants to send. And with that, we can say that the protocol is complete. One of the biggest question we have is that how are we going to create the two entangled photons? Now, one way to do it is via the process called a spontaneous parametric Down conversion, which are essentially saying that there's one photon passing through a nonlinear crystal and will produce two photons. Now, of course, there are several physics laws that they need to apply, such as a momentum conservation and energy conservation law. Next, SPDC can be split into two types, type 1 and type 2, which their difference is essentially their pump angle. So different pump angle will produce type 1 or type 2. And lastly, their difference is also in terms of their equation of states, their outcome, which we can see these two equations are actually Bell state, which we will use it in our next section. Let's talk about quantum teleportation. So starting with the equation of state of entangled photons, which are actually Bell states from the earlier section, Alice can entangle it with her message and measure it to get the result of 0, 0, 0, 1, 1, 0, and 1, 1, which are actually instructions for Bob to apply some kind of Pauli matrices transformation onto his EPR. And these Pauli matrices are, of course, sigma x and sigma z. After that, Bob can actually measure his pair of EPR to get back the message. Now, we have been talking a lot about measuring, and measuring. So what is actually measuring, or how does one measure it? Well, one can actually do that using 3 beam splitters. Well, by passing through these 3 beam splitters and of course one half wave plate, one can actually get a value of 0 or 1. So with that, the quantum teleportation between Bob and Alice are finally completed. Let's look at a simulation for BBM92. We will start by importing the package project Q, and after that, we will define a function such that we can create the bell pair for Alice and Bob. After that, we will also define a function for Alice to entangle her qubit with the message, and after that to measure it. And we know that after measuring it, we get like 0, 0, 0, 0, 1, 1, 0, and 1, 1, and that number will be sent to Bob. So we will have to define another function for Bob to receive the message, process, and to measure it. The processing, of course, is the Pauli X and Pauli Z gate. So after that, we will have to define a function for the whole protocol. So we will have the input of Alice putting in a message, that's the input, and output is the Bob getting the message. All right. So let's look at the result of the simulation. So Alice input the message called 4, and after that she managed to transfer it to Bob, and Bob will measure it and analyze it, and the result is 4 as well. So we can conclude that the simulation is a success. Before we end, let's conclude with a brief summary. BPM92 protocol is made of two parts: preparation of two entangled photons and teleportation. Now in this study, we did not explore more of the practical limitation of quantum cryptography, but that will be left to the future studies. And with that, thank you very much.